Today I will talk about CEBaB, estimating the causal effects of real-world concepts on NLP model behavior. My name is Carl, and this has been joint work together with 3 universities, Stanford, Ghent University in Belgium, and the Technion in Israel. This was joint work with Atticus, Zen, Chris, Eldar, Amir, Yair, and Roy, all authors equal contribution. Our main contribution is introducing a dataset and methodology for comparing concept-based model explanations for NLP models. Model explanations are a prerequisite for trustworthy and safe AI systems. These explanations need to be human interpretable. Humans tend to reason in abstract concepts instead of pixels or tokens. Thus, concept-based model explanations are intuitive. GRACAM, a well-known explanation technique, is not concept-based. This technique aims to highlight the importance of individual pixels or reasons for model prediction. While these results are very interesting, they do not tell us whether or not the model is looking at, for example, the fur of the dog, the leash, the eyes, the ears, the paws, the tail. Contrast this with a concept-based model explanation where specific attributes such as length of the ears or width of the pupils are taken into account. In this case, the authors explain the classifier by investigating how these attributes impact it. If you have access to these high-level concept-based explanations, it's more intuitive for humans to understand, debias, or debug a model. I've shown a couple of examples in the computer vision domain, but the reasoning is also applicable to NLP. For example, we could have a review written in a formal manner or an informal one. We can ask, what is the impact of formality on the sentiment prediction of, for example, a sentiment classifier? There are some key elements throughout this talk that will be repeated, and I'd like to introduce this cast of characters now. We have a model. This could be, for example, a transformer trained on sentiment prediction. We have an input, for example, a restaurant review, and there exists an intermediate concept C latent in the input, such as the formality of the review or specifically what the reviewer thinks about the food in the restaurant. And we cast model explanations as a causal inference problem. An explanation method that is conditioned on the model aims to explain how the model output depends on the specific concept in the input. For example, the explanation method should be able to estimate what the impact of good food, of the concept good food, was on the predicted sentiment of the restaurant review. Thus far, it's been really hard to validate these types of concept-based explanations. To validate this, you need a dataset where you have multiple inputs, where everything else is held constant except the specific concept for which you're trying to estimate the effect. Having these counterfactual inputs allows you to measure the actual change in model behavior. Thus far, there has been no agreed upon large, non-synthetic dataset for this task. This is why we introduce CEBaB. CEBaB is a causal estimation-based benchmark that tackles this problem. We start with restaurant reviews from the OpenTable website. Consider this shortened toy example. Excellent lobster and decor, but rude waiter. And we let human crowd workers annotate the sentence with regard to 4 concepts: food, ambience, service, and noise. For all these intermediate concepts, we have ternary labels: positive, negative, and unknown. In this example, the food and the ambience is rated positive, the service is rated negative, and nothing is said about the noise. We also collect the overall 5-star global sentiment rating for this review. In a subsequent phase, we ask crowd workers to edit these original texts with a specific goal. We ask them to edit the review to only change the expressed value for one intermediate concept, keeping all else the same, and this results in a counterfactual text. For example, for a negative food edit, our example becomes terrible lobster, excellent decor, rude waiter. We again collect the overall sentiment score for this new example. We do this for all texts in the original dataset and for all 4 intermediate concepts. Now we can use these counterfactual texts to start validating explanation techniques. Let's focus on one such counterfactual pair to introduce some notation. This food edit can be used to answer the question, what if the food was negative instead of positive for this given input? We denote the example before the intervention as x with large C equals C, and we denote the example after the intervention with x large C equals C prime. So the large C here denotes the concept on which we intervene. The small c is the concept value before intervention, and C prime is the value after intervention. The first thing we can do, just to understand our dataset a bit better, is to observe the average treatment effect. The average effect of turning food from positive to negative is calculated by aggregating the difference in true sentiment labels over all pairs associated with this intervention. If we do this for all concepts in all intervention directions, we get a table with very intuitive results. For example, for the food concept, turning it from negative to positive in general over our entire dataset increases the overall star label with 1.8 stars. All of these results are very intuitive, and this serves as a first sanity check. There is some real-world effect that is captured by this dataset. Some quick facts. This dataset was crowdsourced by 255 workers. We started with about 2,000 original reviews, and via this editing procedure, we expanded it to a total of 15,000 labeled texts. So now we have counterfactual data, but we still need models. I want to stress that we're not aiming to build the best models here. Our goal is not to get high-achieving sentiment classification models. We just want some models that later on we will try to explain. So the CEBaB data set consists of two parts, a factual part, so the original reviews, and a counterfactual part, all the edited reviews. And we could train a model on all this data, but this would be unfair because most models are only trained on observational data. Therefore, we train the model on this factual part alone. The counterfactual part will be used to validate our explanation methods later. We train and validate BERT, GPT-2, LSTM, and Roberta for the sentiment classification task. Our best models get a macro F1 score of 0.70 on the test split, and now we can start explaining these models. Previously, we calculated the average treatment effect of the dataset. It captures how the real labels change under an intervention on average. We can also study the same effect for our model predictions. This is called the causal concept effect, or cake value, of a given intervention. It is defined similarly to the average treatment effect. For a given intervention, we calculate the average change of model output. Because our models output a vector of probability scores, the cake is a vector as well. For simplicity, we reduce this value to a scalar by considering the labels predicted with highest probability. And so if you calculate these values, we see that they're very similar to the average treatment effect. If you look at these values for the food concept, we see that even though the model was not explicitly trained on this, in general, it behaves in the same way as we expect the real world to behave under interventions. This acts as a second sanity check. The models we consider are good and worthy of further explanation. In the rest of this talk, we will be explaining these model effects. We will ignore the real world effects. Our explanation methods will try to explain model behavior. Even if the model behavior is completely wrong with regard to the real world, if our explainers can explain this wrong behavior, we consider them good explainers. Now we have a dataset that captures some intuitive effect. We also have some models, and we show that they capture this causal effect to some extent. The remaining question is, how can we use this to validate explanation methods? Consider a model, an input, and a corresponding prediction in the form of a probability vector. For this given input, the food is positive. It was an excellent lobster. Now we ask, what if the food was negative? Well, we have that example. We run that through the model and we get another output probability vector. We denote the difference in probability vectors as the I-cake, the individual causal concept effect, the difference between the model outputs on these two examples. And this is the ground truth answer to our what if question from earlier. Typically in the real world, we only have access to the elements in the factual text. And this is due to the fundamental problem of causal inference. And this is why we want to build explanation techniques. Given the original model and the factual inputs, they estimate the answer to these what if questions. Now that we have the CEBaB dataset, we can validate the estimated counterfactual behavior with the ground truth counterfactual behavior. We define the I-cake error, which for a given explanation method measures some distance between the predicted and ground truth model effects. And our goal is to benchmark and to find the best explainers for the first time on a large non-synthetic dataset. We have our dataset, we have our models, we have our methodology. Let us now consider some explanation techniques and investigate the results. We use the following notation for explanation methods. We investigate an explainer with regard to a specific model N based on an input and based on an intervention direction. In this talk, we will discuss 5 methods, a set that is by no means exhaustive. This will give us an initial overview of explanation method performance. As a naive baseline, we consider the approximate counterfactual technique. Here we just approximate a counterfactual input at test time by sampling a random input text that has similar metadata to the desired real counterfactual, and we use this to estimate counterfactual model behavior. A different technique focuses on conditional probabilities. For a given intervention, this method estimates the effect as the difference of average model outputs on examples with the concept value before and after intervention. An interesting method is a conditional expectation learner, S-learner, where we will be approximating the black box with a white box. Given an input, we first predict the values of the intermediate concepts. We train a simple logistic regression model to mimic the black box based on these intermediate concepts. At test time, we intervene on these explicit concepts to simulate interventions on the black box model. For our second to last explanation method, we will consider iterative null space projection, where we will actually alter our model encoder. A concept probe is used to remove information from the encoded representation. Comparing the output of the encoder before and after we remove a specific concept, we can estimate the effect of making a concept unknown in our input. However, this technique can only remove information. Causal LM is a technique that does a similar operation, but instead of removing information from an encoded representation, a whole new encoder is trained with an adversarial objective to ignore a specific concept. So to validate these explainers, we define the I-cake error. This error measures the distance between true and predicted effects. This choice of distance function is flexible. First, we discuss the cosine distance. This function only measures the angle between a true and predicted effect. For example, if our explanation method is really good at understanding which classes will gain probability mass and which classes will lose probability mass, then it will have a very good cosine score. We explore the results on BERT base. Lower scores are better. Two methods that we did not explain in detail, concept CEBaB and TCAF, perform worse than random. This is not necessarily due to the fact that these methods are bad, but can be caused by them not fitting our framework of causal explanations. Causal LM and INLP behave better than random. INLP is better than Causal LM, which is also great because it's conceptually simpler. Conditional expectation and S-learner also behave well, on par with INLP. Interestingly, the approximate counterfactual baseline works surprisingly well, as good as S-learner and INLP. This cosine function does not take the absolute amount of probability mass that gets redistributed into account. That's why we also look at the difference of the norms of these factors. We call this the norm diff metric. For the norm diff metric, the approximate counterfactual technique is the best method. So in conclusion, this naive baseline is our best method that we have across these two metrics. And these results are consistent across BERT, Roberta, an LSTM model, and GPT-2, averaged over 5 different random seeds. We definitely think this is an interesting finding. In conclusion, we introduced a natural data set and methodology for comparing concept-based model explanation techniques for NLP models. The data set and the models trained upon that data capture some real-world effects. Using this data, we can validate concept-based explanation methods. However, we find unsatisfying results for the conventional explainers tested, indicating that there is a lot of future work that still needs to be done. We believe that future work can leverage our dataset and methodology to better understand explanation techniques and subsequently develop more robust explainers. Thank you all for your attention. Feel free to contact us with any questions. Our code is available on GitHub and all our models and data are available on Hugging Face.